And welcome back to another exciting lesson on our journey through calculus. The last couple lessons have been specifically focused on particle motion and how calculus helps us understand how things move around, the position, the rate, the velocity, the speed, all of that. We're going to continue in that theme today. We're going to focus on the idea of acceleration and understanding how acceleration affects velocity. Okay, so with that said, let's go ahead and get started. Our goal, I can determine if a particle is accelerating by calculating the second derivative. We'll talk more about that in a little while. First of all, what is acceleration? Acceleration is the rate at which velocity changes. Acceleration is the rate at which velocity changes. So let's take a step back. What is velocity? Velocity is the rate at which position changes. So velocity is a rate, okay? Acceleration is the rate of velocity. In other words, acceleration is the rate of a rate. It's how quickly your rate changes. So if you were to think about it, if you're in your car and you're looking at your dashboard with all the, the metrics and everything, you've got your speedometer there. And your odometer, right? Your odometer tells you how many miles you have driven. Your tachometer will tell you how many miles you've driven in a certain window, but your odometer tells you how many miles your car has on it altogether. So in a sense, that's like your position, okay? Your speedometer tells you how fast you're going. So when that speedometer says 60 miles per hour, that is your rate, or that is your velocity. I guess it's your speed. It's not your velocity because it doesn't tell you which way you're going. But the numbers tell you how fast you are moving. When you accelerate, your acceleration is the needle moving from one speed to another speed. So you are accelerating when you were going 60 miles an hour, and now you're going 70 miles an hour. So you would say that you have a positive acceleration, okay? Your velocity is increasing, or your speed is increasing because your acceleration is positive, okay? So there's a play there. If your speed changes from 60 miles per hour to 50 miles per hour, then you are decelerating, right? So you are not accelerating, you're decelerating. So your speed is decreasing, which means your acceleration is negative. Your acceleration is negative. So that plays into that relationship a little bit. When we say, for example, when f of x versus f prime of x, we say when f is increasing, that implies that f prime is positive, okay? And then also when f is decreasing, f prime is negative. Now let's relate this to position. So if this is my position function, then this would be my velocity function. So when position is increasing, that implies our velocity is positive. Also, decreasing here implies that the velocity is negative. So that's kind of like one level. But now we need to look at acceleration. And you'll see more of this in the future. This chart, if you would, helps us understand calculus in a very in-depth way. Okay, so when position is increasing or decreasing, velocity is positive or negative. Well, acceleration is the derivative of velocity. So the same relationship that we have here with position to velocity, we have with velocity to acceleration. So instead of murking things up in this column, I'm going to create a different column. When velocity is increasing, that implies that acceleration is positive. And when velocity is decreasing, that implies acceleration is negative. Again, what do we see? We see as velocity changes, as the speed goes up, as the velocity increases, we are saying that we have a positive acceleration because we're seeing the needle move in the positive direction. Same thing here. If velocity is decreasing, we're seeing the needle move in the negative direction. So essentially that needle is your acceleration. If your needle isn't moving, that means your velocity isn't changing, which means your acceleration is a zero. Your acceleration is zero. It's not positive or negative. It's not having an effect on your velocity, okay? So, and I think I just reiterate that here. If velocity is increasing, then acceleration is a positive value, okay? And then vice versa, if velocity is decreasing, then acceleration is negative. All right, so this is important to see. Acceleration is the second derivative of the position function. And we can see that here, that if velocity is equal to the derivative of position and acceleration is equal to the derivative of velocity, then the derivative of velocity would be the second derivative of position. So acceleration is the second derivative of position. All right, so we can say this, and this is a good statement. I have it up here. Acceleration is the derivative of velocity, which is also the second derivative of positions. Now, units for this, units are interesting, and so we should probably explore this a little bit so we understand it. Again, if we understand units in a very in-depth way, it helps us understand applications of calculus. So if I have a graph here where this is my position in respect to time, right? And I say that this is in seconds and then this is in feet, okay? The units here are feet and seconds, okay? If I'm asking for your velocity, the units on velocity, remember, are, so if I've got a graph that looks like this, the change in the y value over the change in the x value. So this is my change in x over my change in t. And so velocity units would be feet per second. We know that. But now let's look at the velocity graph. If I look at the velocity graph, not the position graph, we already know that the units of velocity are feet per second. And our independent variable is still time, and so the units on that are still seconds, okay? So if I were to look at the same graph essentially, but now I'm looking at velocity, the change in the y direction versus the change in the x direction would be a change in velocity over a change in time, okay? So we are saying that acceleration is the change in velocity over the change in time, lowercase deltas here. Well, the change in velocity is a feet per second, and a change in time is a second. And so when I go to simplify this, I end up with something that looks like this. Feet per second times 1 over seconds, right? That's how we divide fractions. And then that becomes feet per second squared. So you could say feet per second or feet per second squared, okay? That's really important. Now, this is a specific example. We have ultimately acceleration is distance over time squared, okay? So that's important. Velocity is distance over time. Acceleration is distance over time squared. So again, examples, meters per second squared, miles per hour squared, and we're not squaring the miles, we're only squaring the time interval, if you would, or the change in time. Okay, so let's go ahead and take a look at an example of this so we can sink our teeth into it and get a good understanding. A particle moves along a line so that its position at any time where t is greater than 0 is given by the function s of t. So s of t is my position, and it tells us that it's negative t cubed plus 7t squared minus 14t plus 8. Okay, so that's my position. And we're going to answer a whole bunch of questions here. I'm just going to let that play out here. Where S is measured in meters and T is measured in seconds. I'm going to write that down. S is in meters and T is in seconds. So let's go ahead and answer a lot of these. This is a good free response question that has a lot of application in calculus. Part A says, find the displacement during the first 3 seconds. Well, what does displacement mean? Displacement means the change in the position over the first 3 seconds. So if I want the change in the position, I need to know 2 things. I need to know where I started, and I need to know where I ended. So over the first 3 seconds, that would imply that I started at time 0. So I'm going to plug in 0 to the time and get a number out. Obviously, when I plug in 0, I end up with 8. And then over the first 3 seconds, so I'm going to plug in 3. Now I'm going to need some work here. So just plugging in 3 to that equation, oops, and then simplifying that and seeing what I come up with. So that's going to be what, negative 27 plus 63 minus 42 plus 8. And so that's going to be, what is that, 36? 36, that's right, minus 34, so that's going to be 2. And so what is our change in position? What's our displacement? Well, if we start at 8 and we go to 2, what does that mean? That means I went backwards. That means I went backwards 6 steps. So our change in position is going to be 2 minus 8, which is negative 6, and it would be negative 6 meters. That is our displacement. That is how far we have moved and what direction I have moved in. So we end up with negative 6 meters for A. Okay? For B, it says find the average velocity during the first 3 seconds. Well, remember the average velocity is just the slope. It is the rate of change over that interval. So what we need to do, average velocity is equal to, over the first 3 seconds, will be s of 3 minus s of 0 over 3 minus 0, right? The average rate of change. Well, we already kind of did all the work over there. S of 3 is 2 minus s of 0 is 8 over 3 minus 0. Now, I do want to point out, average velocity is the change in the position over the change in time. Remember, displacement is the change in position. So we actually already figured out our numerator here. It's negative 6, but I did the work anyways. So negative 6 over 3, which is negative 2. And the units on this guy would be meters per second, okay? Because we have a change in position, which is meters, and a change in time, which is seconds. So negative 2 meters per second. What does that mean? That means over that time interval, I'm moving at a rate of 2 meters, an average rate of 2 meters per second in the negative direction. And that makes sense because I have a negative displacement. I should have a negative velocity there. All right, so that's A and B. Let me make sure I get that right before I move on to the next one. Negative 2 meters per second. Perfect. Okay. Part C, and I'm going to leave the equation up here so I have something to work with here. Part C says find the velocity function. Well, the velocity function, remember, is the derivative of position. Now notice my notation. I want the velocity function. Well, how do I do that? I need to take the derivative of position. So I'm stating that here. I'm not just finding it, I'm stating how I'm finding it. I'm finding it by taking the derivative of that. And then from here we can take the derivative. So we can say that velocity is the derivative. We're just going to use the sum and difference rules and then the power rule. So remember, take the exponent, multiply it to the coefficient, so it's going to be negative 3t, and then subtract 1 from the exponent. Take the exponent, multiply it by the coefficient, so it would be plus 14t. Subtract 1 from the exponent, so that would be 1. I like this one. What's the exponent on negative 14t? Well, that would be t to the first, so use the power rule. 1 times negative 14 is negative 14. T raised to the, subtract 1 from there, we get 0. Well, what is t to the 0? T to the 0 is 1, so negative 14 times t to the 0 is just negative 14, right? And so we end up with that guy. And then obviously the derivative of a constant 8 is 0. So this is my velocity function. I don't have to put t to the first, I can just put t there. Okay? So that's my velocity function. Let's make sure that is correct. Negative 3t squared plus 14t minus 14. Perfect. And then part D, it says find the velocity at t equals 2. So we're really looking for v of 2. Now remember in part B it was saying what is the average velocity over the first 3 seconds. So we were finding out the average rate of change over a time interval. Here we're finding the actual rate of change, the real rate of change at this moment in time. Now they may be the same, it may be related, they may be close, but they don't have to be. Okay? So v of 2, I'm looking for the instantaneous rates or the velocity when t equals 2. So we'll just plug that into my velocity function. So that would be negative 3 times 2 squared plus 14 times 2 minus 14. So that's going to be 4. That would be negative 12 plus 28 minus 14. So that's 14. So that's going to be 2 right there. So that's going to be 2 meters per second. So what does that mean? That's interesting. That's interesting. Because remember in part B it says over the first 3 seconds our average rate was negative 2. Which means over the first 3 seconds, we are saying we're heading in the negative direction. We're going backwards. But here at t equals 2, which is at some point between t equals 0 and t equals 3, we're actually heading in the positive direction because the rate is positive here. So that means somewhere in there I had to turn around because at that moment I was heading that way, but overall I was heading that way. Okay, so that's an interesting thing to figure out and to discuss, okay? Part E, it says find the acceleration function. Well, we know that the acceleration function, I'll just do it right here, the acceleration function is the derivative of the velocity function, so I'm going to express that here. A of t is equal to v prime of t. Now, I could also say it's the second derivative of acceleration, but because I've identified what velocity is here, I only have to go to that point. So A of t is going to be equal to negative 6t plus 14. Again, power rule there. So there's my acceleration function. Make sure I'm right there. So negative 6t plus 14. Part F, it says find the acceleration at t equals 2. I like where this is going. This is going to be an interesting idea here. Acceleration when t equals 2. That just means I plug in 2 to my acceleration function. So it's negative 6 times 2 plus 14, which is negative 12 plus 14, which is, interestingly, 2. Now the units on this are going to be, remember, meters per second squared. That's my acceleration there. It is coincidence that these numbers are all working out to be pretty much the same value. I did not intend that and don't think that it's a pattern that is true in all position velocity acceleration relationships. Okay. Part G, let me talk about part F and part D real fast because this is going to be something that's going to extend into the future. Okay. I want you to understand what's happening at t equals 2. We have a pretty good understanding of what's going on based on these two things. When t equals 2, my velocity is 2 meters per second. What does that mean? That means I'm heading in the positive direction at a rate of 2 meters per second at that moment. That's how fast I am going. I'm going 2 meters per second in the positive direction. Acceleration is also positive 2. Okay? That means acceleration is essentially a force, and we'll get more into that in the future. Acceleration is the idea of a force. In other words, it's something that is either pushing us forward or pulling us back. Okay? So if I am heading this direction, because my velocity is positive, okay, I'm moving in that direction, and I have a force on me that is propelling me or pushing me in the positive direction, so I'm running along this way, and I have basically, in a sense, something coming up behind me and exhibiting a force on me to move me in the positive direction. What does that imply? That implies that I am actually speeding up at that time. Since my velocity is positive, I'm heading that way, and I have the force of acceleration that is pushing in that same direction. It's forcing me to speed up. Okay? Now watch the opposite of this. Let's say that velocity at a specific point in time, at 2, was positive, right, greater than 0, and my acceleration is negative. Let's say that was the case. Well, that would mean I'm heading in the positive direction, I'm heading that way, but I have a force of acceleration that is pushing me this way. Okay, so I'm moving that way, but I have something that's fighting against me this way. So what does that mean? That means I would be slowing down. So if I'm heading in this direction, but acceleration is pushing the other way, then I am slowing down, okay? We'll get, again, more in depth with this later, but I'll do one more example of this. Let's say both of them are negative. Let's say velocity is negative and acceleration is negative. Well, if velocity is negative, that means I'm heading in the negative direction, okay? Now, acceleration is negative. Well, which way is negative again? Negative is that way. So acceleration is causing me or asking me essentially to move in that direction. So I'm going this way, and then I have acceleration pushing me that way. That would imply that I'm speeding up again, okay? So you can see that if velocity and acceleration are both positive, then I'm speeding up. If velocity and acceleration are both negative, then I'm also speeding up, okay? Bottom line is, if velocity and acceleration have the same signs, you're going to be speeding up. And if velocity and acceleration have different signs, then you'll be slowing down. We'll talk about more of that in the future. Part G says, when is the particle at rest? Well, what does that mean? At rest. At rest, by definition, means that, I guess you could say you're not moving. Well, how do I not move? That implies that my velocity is zero. My rate is zero. So I am at rest when v of t equals 0. I'm not moving when my velocity is 0. That makes sense. So what I have to do to figure out when I'm at rest is to take my velocity function and set it equal to 0. Now, trying to understand that correlation, that's an important thing. If you were to think that, oh, I'll make acceleration equal to 0, well, what does that mean? If my acceleration were 0, that would imply that whatever my velocity is, it's not changing. So again, I'm going maybe 60 miles per hour. If my acceleration is 0, that means my velocity stays at 60 miles per hour. It's not changing. So I'm not at rest then. I am moving. I am just moving at a constant rate if my acceleration is 0. If my position is 0, if I set my position equal to 0, that means I'm on the origin, I'm at home, I'm wherever we consider 0. So if I set my position equal to 0, I'm just looking for the times that I am at my origin, essentially. So at rest is when velocity is 0. And so then we need to solve this equation through whatever method. I believe I set this up, or I made this problem so that it's factorable. So we know the factors have to have a negative 3t and a t, or maybe a t and a negative, or a negative t and a positive 3t. Let's see what happens here. 7, does this factor? Let's see. Excuse me. 28, 38, 42, and 14. Boy, going back to math 2 to figure this problem out. Look at that. 3 times 14, yeah. 4 doesn't work, 5 doesn't work, 6 works, 6 and 7. I don't think this is factorable. Let me check my answers here. Particle is at rest. Oh, no, it's not factorable because you can see those answers there. So this part is actually going to be a calculator problem. Now, if you want, you could use the quadratic formula, but I'm not going to do that. This is a calculator problem. So we're looking for when velocity is 0. What am I going to do here? That implies I'm going to type in my velocity function into my calculator, or into my y-list. So that's going to be negative 3x raised to the second plus 14x minus 14. So I have that saved into my y-list, and I'm going to go ahead and graph this. I want to change my window. Now it said, the domain said t is greater than 0. So I'm going to change my window from 0 to my maximum. Maybe I'll go to 30. Noticing that this is a parabola, so I could get up to 2 zeros out of this. And I can see it pretty easily. The graph looks something like this. Looks something like that, okay? So this is the graph of velocity. Where is velocity equal to 0? That would be here and here. So we're going to take our calculator, find our zeros, have our lower bound here. If I can find my cursor. My cursor's hiding from me. Change my window to 10. That way I see a little bit better of the graph. There we go. Okay. So 0 And we'll go to the left at 1, and then to 2 is the right. So we got t equals 1.451, and then we'll find the other 0. Lower bound, upper bound, and we end up with 3.215. If you need help doing that with the calculator, I have a lesson in my Unit 0 of calculus that will show you how those keystrokes are for getting those zeros. So anyways, that is when the particle is at rest, at these times. Now, some people might say, well, you're not actually at rest because you never actually stopped and sat there for a minute. But the definition of at rest is when the velocity is 0. So these are singular points in time. Okay. All right, so we have that correct, and the units would be seconds, right? I guess I forgot to mention that. So we are at rest at those 2 times. And then part H, it says, when does the particle change directions? When does the particle change directions? The particle changes directions when velocity changes signs. And so what we look at here to determine this, to think through this, if I'm heading in that direction, my velocity is positive. How is it that I change directions? Well, in order to change directions, I need to start heading that way. So I'm walking in the positive direction, and all of a sudden I turn and I go in the negative direction. When do I change directions? I change directions when velocity changes signs. So what I do here is I set up a number line, and I know that I have an endpoint of t equals 0, according to the domain restriction in the problem. And I know that velocity is 0 at these 2 points, at 1.451 and 3.215. And there is no end to our time. It just says t is greater than or equals 0, so we'll keep it going that way. Now, if I'm looking at the velocity function, I know that velocity is 0 at these 2 points. Those are the only zeros I had. So I can't get any other zeros, which means whatever sign velocity is in this interval, or at any point in this interval, will be the same throughout that entire interval. Because if it changed, if it was velocity was positive and then it went negative, that would imply that I have another 0 somewhere in there. And I don't. I only have 2 zeros. This is a quadratic. I can only get up to 2 zeros. Now, when I look at the graph, like I said before, if I'm looking at this graph, I had a parabola that looks like this. And if this is my velocity function, I see that my velocity is negative in this region. So I'll put a negative sign there. And then it's positive in between the 2 zeros. And then it's negative to the right of 3.215. So now I have this number line here. Okay. Well, what's happening? This is telling me that my velocity is negative from 0 to 1.451. So I'm walking along for 1.451 seconds in that direction. Then I stop instantly. Well, not instantly. I actually slow down and then speed up again. But I stop at a moment. I turn around and I start walking in the positive direction. Okay? And then at t equals 3.215, again, I change directions because now my velocity is negative. So the justification that I want to use here is this. I would say the particle changes direction when t equals 1.451 seconds and 3.215 seconds. Oops, can't spell. And then now we want to provide justification. Since velocity, v of t, changes signs at these times. That's really what we're looking for when we're looking for a change in direction. The particle changes direction when the velocity changes signs. This is not going to be sufficient for work, for your answer. Just finding the zeros doesn't necessarily mean that that's where it changes direction, because let's just look at this hypothetically. If that was positive, if the velocity here was positive and the velocity here is positive, what's taking place there? It means that I'm heading in the positive direction, and then I slow down to a point where my velocity is 0, so I stop for a split second, and then I go into the positive direction again, so I can just continue on my path. So I'm moving in the positive direction, I stop for a split second, and then I keep moving in the positive direction. Then over here is where I change directions because velocity changes signs. We cannot say simply because velocity is 0, we will change directions. It's like heading down a road and I get to a stoplight and I just want to go straight, right? I hit the stoplight, so I stop, and then when the light turns green, I keep going in the same direction. My velocity was 0 while I was stopped. That doesn't automatically mean I turned around. It just means that I stopped, okay? So we have to check to see if velocity changes signs. That's the important part. Not just that it's 0, but that it changes signs. All right, let me make sure that is correct there. And again, it's just kind of coincidence that those answers are the same as those ones. Don't think that that is always the case, because it's not. So let's go ahead and take a look at another example of how this relates. We have here a graph instead of a function. But notice the key important thing about this graph is that this is the graph of the velocity function, okay? That's important. Essentially, I gave you the derivative graph, and we have to interpret what's going on based on that graph, okay? So I'm going to do my best at graphing this, and I'll use a different color here so that we can see it a little bit better, hopefully. So we've got something that goes up and then goes down, and then flattens out, and then goes down again, okay? So the intervals here, we've got 2 there. That's going to be 1. That's going to be 4, and then all the way to 6, and then to 9 over here, okay? So this is not exact by any means, but it gives us an idea or something that I can point out. All right, so I have given you the velocity function, and I'm asking for, a bunch of different things, like 10 different things, okay? The first question, it says, when is the particle moving forward? Well, what does it mean to move forward? It means to move in the positive direction. Well, how do I know when I'm moving in the positive direction? I am moving in the positive direction when my velocity is positive. Now, if I give you the position, right, how would I know I'm moving forward? Moving forward when position, x of t, is increasing, right? Moving forward when position is increasing. But what does that mean for velocity? It means moving forward when velocity is positive, okay? So that's the relationship there. Because I was given the velocity graph, where is velocity positive? Velocity is positive when velocity is above the t-axis in this case. So we would say for A, we're moving forward over the interval 1 is less than t is less than 4. And we could say since v of t is greater than 0, is positive. Okay, so that's when we're moving forward. Part B says, when is the particle moving backwards? So when are we moving in that direction? So moving backwards, that's the exact opposite of this. That would imply when velocity is negative, because remember, velocity always gives us direction. So velocity is negative over the interval 0 to 1 and 6 to 9. And the justification would be since v of t is negative or less than 0. Okay. For part C, it says, when is the particle speeding up? Now this question, the idea of speeding up can be a difficult concept to wrap our heads around. We'll go more in depth with it in the future, but I want you to understand speeding up. What does that mean? Well, remember, speed is the absolute value of velocity. Okay? So that means whatever velocity is, speed is going to be the positive version of that. So if velocity is positive, speed will be positive. If velocity is negative, speed will be positive. It'll just be the same numeric value with a positive sign. But how do I know I'm speeding up? Or in other words, another way of saying that is, when is my speed increasing? Okay, when am I getting faster? Well, there's two scenarios that I can get faster with. Okay. First of all, it depends on which direction I'm going. It does not matter where I'm at. It doesn't matter my position. What matters is which direction I'm going. So if I'm moving in the positive direction, how is it that I can move faster? I move faster when I have a force that propels me to go in the same direction, or to move faster in the same direction. That force is acceleration. So velocity being positive tells me I'm going this way. I need something to propel me in that direction, and that is acceleration. So if acceleration is pushing me in the same direction that I'm going, then I'm going to speed up. So I'm running along, and essentially I have something that's pushing me to go faster. So the bottom line is, if velocity is positive and my acceleration is positive, that means I'm going to speed up. Same way going the other way. If my velocity is negative, I need something that's going to propel me in that direction to go faster. Well, that would be acceleration. Acceleration would have to be negative also. So if I'm speeding up going backwards, that means my velocity is negative, and my acceleration would also be negative. Watch what happens when I'm slowing down. Slowing down would be kind of the opposite. If my velocity is negative, I'm heading that way, well, how do I slow down? I have a force that is pushing against me, so that's causing me to slow down, okay? So if my velocity is negative and my acceleration is positive, so it's kind of like wind, it's pushing against me, then I'm going to slow down as a result of that, okay? And then going this way, if my velocity is positive, if the wind is going against me, or if the acceleration, that's not the best way of saying it, but if the acceleration is pushing against me, then I'm going to slow down. The bottom line is, if velocity and acceleration have the same signs, then the particle or the object would be speeding up, and if the velocity and acceleration have different signs, then the object will be slowing down, okay? But how do I look at velocity and acceleration, because I'm only given the velocity graph? Well, let's see here. Let's make a comparison. We would say velocity, we want to know when velocity is positive. We want to know when velocity, we want to know when velocity is positive and when acceleration is positive. And we want to know when velocity is negative and acceleration is negative. If velocity and acceleration have the same signs, then I'm going to be speeding up. Well, I know how to tell when velocity is positive. I just answered that in part A. In part B, it's positive when it's above the x-axis. How do I know when acceleration is positive? Well, remember that acceleration is the derivative of velocity, okay? So really, when I'm saying when is acceleration positive, I'm asking for when the derivative of velocity is positive. Well, how do I know when a function, in this case velocity, when its derivative is positive? The derivative is positive when the slope of the function is positive. In other words, when the function is increasing. So we would say this: velocity is positive and acceleration is positive when, obviously velocity is positive, we're going to rewrite that, and velocity is increasing. Okay, when velocity is increasing. Because if velocity is increasing, that implies that acceleration is positive. Okay, same thing over here. We can reinterpret this to say when velocity is negative and when velocity is, well, if acceleration is negative, that implies that velocity is decreasing. Okay, velocity is decreasing. So essentially, we're looking for when the graph of velocity is positive and increasing. So we see that from 1 to 2, 1 to 2, and, or when velocity is negative and decreasing. So here we see velocity is negative, but velocity is increasing there, so that doesn't work. Velocity is negative and decreasing there, so we'd say from 6 to 9 as well. And the justification for C would be that velocity and acceleration have the same signs, because velocity is positive and increasing or negative and decreasing. Again, we'll get more into that in the future, but it's just a good introduction to the idea. And then when we get to part, it says when graph the acceleration or graph the speed on part I, I'll explain how that relates to part C here in part D. Part D says when is the particle slowing down? Well, we're slowing down in the exact opposite manner. We're slowing down when velocity is positive and acceleration is negative. They're fighting against each other. I'm going that way, but acceleration is pushing me this way, so I'm slowing down. So this would imply that velocity is positive and decreasing. Okay? In the opposite way, if velocity is negative, that would imply we want acceleration to be positive, because if I'm heading that way, I would need acceleration to be pushing against me for me to slow down. So therefore, we would say when velocity is negative, and if acceleration is positive, that means the derivative of velocity is positive, which means velocity is increasing. So we're looking for one of these two scenarios. When is velocity positive and decreasing? That is from 2 to 4. And then when is velocity negative and increasing? Well, it's negative and increasing from 0 to 1. Okay, so that's the answer for part C and D. Again, I'll try and explain that through the speed graph in just a minute. Okay, so for part E, it says, when is the acceleration positive? Well, remember, like I said just a second ago, acceleration is the derivative of velocity. So acceleration is positive when the derivative of velocity is positive. Well, when is the derivative positive? The derivative is positive when velocity is increasing. Okay. So acceleration is positive when velocity is increasing. So velocity is increasing from 0 to 2. Okay. And there's your justification for that. All right, for F, when is the acceleration negative? Well, it would be the opposite of this. Acceleration is negative when v prime of t, because that's acceleration, is negative, which implies that v is decreasing. V is decreasing. So if you see v decreasing, then our acceleration is negative. So we'd say from 2 to 4 and from 6 to 9. Okay? So that is when acceleration is negative. G, when is the acceleration 0? Well, again, we're looking for when the derivative of velocity is 0. So when is the derivative of this graph 0? It's when you have a horizontal tangent line. So a lot of times you see horizontal tangent lines when you have a peak or a valley, but that's because it's nice and smooth. Here we have a corner, so we don't have a horizontal tangent line there. It's not differentiable at those corners. But we do have horizontal tangent lines here because velocity is horizontal throughout that entire region. So we would say from 4 to 6, that is when acceleration is 0, because that's when the slope of that graph is 0. All right, for H, when does the particle at its greatest speed? That doesn't even make sense. And there's the bell. When is the particle at its greatest speed? Now, it would be nice, I guess it would have been nice to graph the speed function, and we'll actually do that later, but I want to try and interpret it without the speed graph. When is the particle at its greatest speed? Well, this is velocity. Speed is the absolute value of velocity. So in order to find the greatest speed, I would have to find the greatest velocity and the lowest velocity. Because if, let's say, velocity is negative 20 at one point, and velocity is 10 at another point, well, obviously 10 is greater than negative 20. So the greatest velocity in that case would be 10. But if I'm asking for greatest speed, you would say that the speed when the velocity is negative 20 is 20, and the speed when velocity is 10 is 10. So then the greatest speed is 20, because that is further away from 0, essentially. So the greatest velocity is when t equals 2. The least velocity is when t equals 9. Okay? So now we have to compare those. Well, which one has the greatest speed? It would be the one that is furthest away from the t-axis here. So we'd have to refer to the actual graph to get a little bit more scale. So we would say, well, let's see, maybe the velocity here is like negative 5, and then 0, and then maybe this is, I don't know, it's a line. So let's say that's 5, and then back to 0 again, 0, and then velocity, oh, velocity goes way down here. Maybe that's like negative 10, right? So we've got a velocity of 5 and a velocity of negative 10. Well, that would imply that the speed at 2 is 5 and the speed at 9 is 10. So the greatest speed occurs, in this case, when t equals 9. Okay? And then for I, it says graph the particle's speed. Well, the particle's speed is, again, the absolute value of velocity. So all I have to do to this graph is to flip it up. So everything that is above the x-axis or the t-axis will remain the same. Everything at 0 will remain the same, but everything below the x-axis has to reflect up. So it would look something like this. Okay? That would be my speed graph, essentially. 9 and 6 and 4 and 2 and 1. So that's my speed graph. Now, I did want to relate that speed graph to part C and part D, because part C said, when is the particle speeding up? Well, if this is my speed graph, my speed is increasing whenever you see this graph going uphill. Well, we see that this is going uphill from 1 to 2, and it's also going uphill from 6 to 9, and that's exactly what I got in part C. When am I slowing down? That is when the speed is decreasing. So if this is the speed graph, that would be from 0 to 1 and from 2 to 4. Yeah, 0 to 1 and 2 to 4. I just have them written backwards there. Okay, so you can see it actually in the speed graph a little bit easier, but we need to be able to interpret speeding up and slowing down when we have analytic approaches, when we have graphs that aren't necessarily related to the thing that I'm asking about. Okay, so that's I. And then J is going to be the derivative, and I'm going to put that up here because I want to put it right next to the velocity graph. So 1, 2, 4, 6, and 9. Okay, so the question in part J says, graph the particle's acceleration, A of t. Okay, so the particle's acceleration, remember, is the derivative of velocity. So we just got to figure out the slopes of this guy. Now, conveniently, these are all linear functions, so we can find the slopes pretty easily. Now, we don't know the y values, so we can't find the actual slopes, but we can get a good estimate. We know that the slope from 0 to 2 is a constant slope. So the derivative of a line, remember, is a constant. Okay? So since this is increasing, this guy is going to be positive from 0 to 2. Okay? Okay? And because that's linear, this is a constant. From 2 to 4, we see that velocity is decreasing at a constant rate. Okay? Therefore, the derivative, the acceleration, will be negative from 2 to 4. From 4 to 6, we see that we have a slope of 0, so then our acceleration will be 0 in those places. By the way, again, this is just coincidence. Just because velocity is 0 throughout the whole region doesn't, if this horizontal line was up here, then the acceleration would be 0 still here. Okay, it doesn't match that height essentially. Okay, and that should make sense. And then we can see from 6 to 9, looking at the original graph, it looks like it's kind of the same rate as the previous 2 to 4. So that would be something like this. Okay. Now notice what happens here. When you have a function that has corners on it, then the graph of its derivative has a bunch of discontinuities. So we have a corner at 2, jump discontinuities. Therefore, we have a jump discontinuity at 2. We have a corner at 4, so we have a jump discontinuity at 4. We have a corner at 6, so we have a jump discontinuity at 6. All right. So that is the example looking at a graphical approach. And I'm just going to quickly look at the answers to make sure we did that all right. Looks good there. And then 1 to 2 and 6 to 9. D is 2 to 4 and 0 to 1. And then 0 to 2 for E. 2 to 4 for F and 6 to 9 for F. G is 4 to 6. And then T equals 9 is H. And then I, the speed graph, again, is just going to take all the negative velocities and flip them up and make them positive. And then for the acceleration graph, we're going to have horizontal lines everywhere because these are all linear functions and the slopes are constant. Okay, so we get something, oh, what did I do? I do have something wrong there. Ha-ha! Uh-oh. Teacher messed up. Right here from 6 to 9, this graph is decreasing, therefore this slope should be negative here. Okay, and again, we don't know the exact slopes there, so these are just estimates, but you get the idea. All right, last problem here, exit problem. This is going to take the particle motion, apply it in an analytical sense, okay? It gives us the function of velocity, and it tells us to, what does it tell us to do here? For what values of t is the speed of the particle increasing? All right, so velocity equals 5 cosine of t minus 2. And we're looking for the over the interval 0 to 2 pi. All right. So we want to know when the speed of the particle is increasing. Now remember, we just went through that whole scenario. How do I know when speed is increasing? Speed is increasing when velocity and acceleration have the same sign. Now that's going to be important. Speed is increasing when velocity and acceleration have the same sign. In any problem in calculus, we have to get to a point where we can analyze the signs of a function. Okay? So we need to figure out when the velocity is positive and negative, and we also need to figure out when the acceleration is positive and negative. Well, if I'm looking at the velocity function, I can figure out where that's positive and negative pretty quickly. But this is a calculator-based problem. So I'm going to go ahead and type into my calculator, into the y-list. I'm going to type in 5 cosine of x minus 2. And I'm going to look at the window from 0 to 2 pi. And then I'll just roughly graph it here. So we have a reference. Okay. And we have something that looks like this, like a cosine graph. Our graph is actually going to be shifted down a little bit because of the negative 2, and it's got a higher amplitude or greater amplitude because of that coefficient out front. But what we need to do in order to figure out when the velocity is positive and negative, well, we can see it's positive in this interval, negative in that interval, and positive in that interval. The real question is then, when does it change signs, right? And it changes signs when velocity in this case is 0. So our first step here is to set velocity equal to 0. Okay? Set velocity equal to 0. I don't expect you to solve that analytically. I expect you to use your calculator. So I'm going to go ahead and hit F5 and 0, and I'm going to move my cursor to the left of my first x-intercept, and then I'm going to hit enter, and then it's asking for the upper bound, so I'm going to move it to the right. And so I end up with two values, t equals 1.159, and then I've got to do the other 0. That's going to be, let's say, 8 there. Oops. Pushing the wrong buttons. Lower bound and 6. How about that? All right, so we end up with 5.124. So these are the two values when the velocity is equal to 0. Okay, and by the way, if you don't know how to use your calculator to find the zeros, I have a video on that in the introductions playlist for calculus. All right, so I should have probably not erased that graph, but I like to create a number line. This is so essential in understanding what's taking place in these types of problems. So 0 to 2 pi, because that's my interval, and then we know that we had a 0 at 1.159 and another 0 at 5.124. So that is when the velocity is 0. Okay? So we can read it this way. We can say that when time is whatever this is, the velocity is whatever these are. Okay? Now we know the velocity is 0 at this time and at this time. I don't really care where the velocity is 0. I care where the velocity is positive and negative. And since I looked at my graph, and I had a graph that looked like that, and so that was my first 0, and that's my second 0, I can say that the velocity is positive in that first interval, negative in the second interval, and positive in the third interval. Again, don't get used to the idea that the signs always change. They don't always change. Sometimes it goes positive, then 0, then positive. All right. Since we are looking for when velocity and acceleration have the same signs, well, I have the signs for velocity now. Now I need to figure out the signs for acceleration. So, and I'll go back to the justification in a second. I need to figure out the acceleration function in order to figure out the signs of acceleration. So how do I find the acceleration function? I have to take the derivative of the velocity function. So I got to take the derivative of this guy. Well, here, what do I notice? I notice that I have a constant multiple out front. I have cosine of t, and then I have a minus 2. So I have a sum and difference rule here. This one's going to be easy. The derivative of negative 2 is 0. This guy, hopefully you recognize this as something where you can apply the product rule because I'm multiplying the 5 times the cosine. So if I take the derivative using the product rule, the derivative of the first thing is 0, derivative of 5 is 0, times the second thing, plus the derivative of the second thing. Well, what's the derivative of cosine? The derivative of cosine is negative sine, and then times the first thing, so times 5. This all simplifies to negative 5 sine of t, because the 0 cancels that out, and I just move the 5 in front. So you can use the product rule there, and you should be able to recognize that you can, right? The biggest issue with product rule is students not recognizing when it's applicable. Anytime you have multiplication, it's applicable. But we could use the constant multiple rule. Remember, the constant multiple rule said, if I want the derivative of this guy, of a constant multiple times a function, that's the same as taking, let me go ahead and write this down, d dt of 5 cosine of t. That's the same as taking the constant multiple out and then taking the derivative of the function, which is negative sine of t, and then multiplying it by the constant. So either way, the derivative, or the acceleration in this case, is going to be negative 5 sine of t. All right. Well, we want to figure out the signs of this guy, so we're going to do the same thing we did on velocity. We're going to set it equal to 0. Now this one's solvable without a calculator because this is, I'll just divide by negative 5. And when is sine equal to 0? Sine is equal to 0 when t equals 0, pi, and 2 pi. Okay? Now if you need your calculator for that, that's fine because the whole problem is a calculator problem. So now I'm going to set up my number line for acceleration from 0 to 2 pi. And then pi, remember, is 3.14159. 142, I'll say. So this is when t equals these values. My acceleration, so I'll use red for acceleration, is 0 at those 3 values. Okay? Really, it doesn't matter if it's 0 at the ends. Those are endpoints. But now we need to think about the signs of this guy. This is a negative sign graph. So instead of going up to start, it's going to go down to start. So it's going to look something like that. Well, we have a negative acceleration because it's below. We have a positive acceleration because it's above. So we have negative and positive there. And again, if you looked at your calculator to do that, that's fine. But now remember what we're looking for. We're looking for when the particle is speeding up. When is the speed increasing? Speed is increasing when velocity and acceleration have the same signs. So if I just look at these intervals on the velocity, velocity is positive over that interval. Well, over that same interval in acceleration, it's negative. So we're not speeding up. In this interval, we're actually slowing down because the velocity and acceleration are different signs. From 1.159 to 5.124, we have a negative velocity, so we should have a negative acceleration in that window. Well, we do for part of it, but we don't in the other part. So what part has negative and negative for both of them? Well, that would be from 1.159 less than t less than 3.142. We can see that the velocity is negative within that window and the acceleration is negative within that same window. Okay, so therefore we're speeding up. For the next window from 3.142 to 5.124, we have opposite signs. So therefore we're slowing down within that region. From 5.124 to 2 pi, we have a positive velocity and a positive acceleration. So we would say and 5.124 less than t less than 2 pi. This is where we're speeding up. We would say speeding up, speed is increasing. Speed is increasing over those intervals. And now our justification, since v of t and a of t have the same signs within those intervals. All right. So that is our answer for this problem here. Now let me double check to make sure I have that correct. 1.159 to 3.142 and 5.124 to 6.283, which is 2 pi. Okay. Again, we'll go more in depth with this idea later on, but we actually did go pretty deep. So hopefully you have a pretty good understanding of this. It was a lot of work. This video was extremely long. You probably noticed right in the middle of the video that my shirt changed. It was so long because I did half of it on one day, and then my camera decided not to work anymore that day. And so I had to finish up the video for the next day. But anyways, if you have any questions on any of this particle motion stuff, please ask. Do not put yourself in a position that you think like, okay, I can't ask this question because it seems, it'll make it seem like I don't know what I'm doing. Well, if you don't ask the questions and you don't know what you're doing, you will continue not knowing what you're doing, and it will become more and more evident as time goes on. So when you are struggling with something, as I'm sure some of you probably are with this, you need to reach out and ask for the help. And you do that by commenting or reaching out to me during tutoring. So with that said, have a great evening. I'll talk to you again next time.